Right now, at this very moment, there are two machines drifting through interstellar space, not one, two. Most people have heard of Voyager 1, the farthest human-made object ever built. The spacecraft that broke through into interstellar space back in 2012 and has been feeding us data from beyond our solar system's edge ever since. It's the one carrying the golden record, the one that keeps making headlines, the one everybody talks about. But there's a second spacecraft out there, quieter, less celebrated, rarely mentioned, moving through the dark, roughly 13 billion miles from Earth in an entirely different direction, sampling a completely different slice of interstellar space and carrying something Voyager 1 lost before it ever reached the heliopause, something that turned out to be the single most important instrument for understanding what actually happens at the edge of our solar system. It's called Voyager 2. And what it found the moment it crossed into interstellar space, what its unique, one-of-a-kind instrument measured as it passed through a boundary no model had ever correctly predicted, didn't just confirm what Voyager 1 discovered. It contradicted parts of it. It complicated the picture. It raised questions that Voyager 1, for all its remarkable achievements, simply had no way of answering, because Voyager 1 was blind to the single most important measurement at the heliopause, and Voyager 2 was not. And right now, in the summer of 2026, Voyager 2 is on the verge of becoming the most consequential spacecraft in the entire history of this mission. Not purely because of what it's found, but because of what NASA is about to attempt on it. A procedure so risky, so unprecedented, so thoroughly all or nothing, that the engineering team nicknamed it the Big Bang. A simultaneous, coordinated overhaul of every remaining power system aboard the spacecraft, executed across a communication delay exceeding 16 hours in each direction, with no backup plan and no second attempt if anything goes wrong. If it succeeds, Voyager 2 buys itself more time. And everything NASA plans to try on Voyager 1 come July hinges entirely on whether Voyager 2 survives what happens first. Stick with me, because this is a story almost nobody has heard, and it matters more than anything else currently being said about the Voyager mission. Voyager 2 launched on August 20th, 1977, 16 days before Voyager 1. Despite carrying the higher number in its name, that's not a mistake or some clerical slip. It reflects the order in which the two missions were expected to reach their respective destinations. Voyager 1 rode the faster trajectory, aimed at a path that would sweep it past Jupiter and Saturn, before angling it out of the solar system entirely. Voyager 2 was handed a longer, more intricate route, one that would let it do something Voyager 1 never could, something that, at the time of launch, no spacecraft had ever accomplished, and that, nearly 50 years later, still no other spacecraft has matched. Voyager 2 remains the only spacecraft in human history to have visited all four outer planets, Jupiter, Saturn, Uranus, and Neptune, every single one of our solar system's gas and ice giants, observed up close, in detail, with instruments built to read their atmospheres, magnetic fields, and moon systems. Voyager 1, by contrast, visited Jupiter and Saturn, then peeled off northward out of the ecliptic plane, trading away any shot at Uranus and Neptune in exchange for a closer flyby of Saturn's moon Titan and a faster route toward interstellar space. That was a deliberate choice. Two spacecraft, two missions, two very different answers to the question of what the outer solar system actually looks like. The price Voyager 2 paid for touring all four planets was time. Its path, shaped by gravitational assists from each planet in sequence, simply took longer to unfold. Voyager 1 crossed the heliopause in August 2012. Voyager 2 didn't cross until November 5, 2018, 6 years and 3 months later. For those 6 years, Voyager 1 sat alone in interstellar space, measuring plasma and magnetic fields beyond the boundary, sending back data that was already confounding scientists and forcing a rethink of existing models. But the story it told was incomplete, because the one instrument that would have let Voyager 1 tell the full story had stopped working back in 1980. Here's the detail almost nobody brings up when discussing what Voyager 1 found at the heliopause: its plasma science instrument, the device built to directly measure the temperature, density, and flow velocity of plasma both inside the heliosphere and out in the interstellar medium, died in 1980, not at the heliopause, not in interstellar space. It failed before Voyager 1 had even reached Jupiter's orbit on its outbound leg. 4 full decades before the spacecraft ever crossed the heliopause, before any of the interstellar science even began. The one instrument that would have mattered most for understanding what the heliopause actually looks like from the inside had already gone dark. That meant when Voyager 1 finally crossed the boundary in 2012, it did so unable to directly measure the plasma on either side. Scientists had to infer what was happening using other instruments, the cosmic ray detector, the magnetometer, the plasma wave subsystem, but they couldn't measure the plasma itself. They were working around a hole in the data, one that had existed for 32 years by the time the crossing finally happened, and one they simply couldn't fill. Voyager 2's plasma science instrument, on the other hand, was still alive. When Voyager 2 crossed the heliopause on November 5, 2018, it carried a fully functioning plasma sensor, the very instrument Voyager 1 had lost before the Cold War even ended. At that boundary, it produced a dataset researchers would go on to call historic, the first ever direct simultaneous measurement of plasma on both sides of the heliopause, inside the heliosphere and out in interstellar space, captured at the exact moment the spacecraft crossed the line. 5 papers published together in Nature Astronomy in November 2019 laid out what Voyager 2's instruments had found at the heliopause, and what they found contradicted the models in ways that genuinely stunned a field that had spent 6 years working with Voyager 1's incomplete picture. The first surprise concerned the thickness of the boundary itself. Scientists had expected the heliopause to be a fairly thin, sharp transition, a defined line where the solar wind ends and interstellar space begins, with models placing it at maybe a few 100,000 kilometers wide, a narrow zone where hot, fast solar wind meets cold, dense interstellar plasma, and the two blend briefly before separating. What Voyager 2 actually found was a distinct transitional layer roughly 100 million miles wide, sitting just outside the heliopause, not on the solar wind side, but out in what was supposed to be pure interstellar space, where interstellar plasma was expected to begin immediately. Instead, Voyager 2 detected a region where interstellar particles had pushed inward through the boundary like roots, working through rock, tendrils of interstellar material reaching more than 100 million miles inward, mixing with the solar environment in ways no model anticipated. Voyager 1 had glimpsed something similar before its own crossing, but different in character. On approach, it had entered a region where the outbound solar wind had slowed nearly to a standstill, a stagnant zone just inside the boundary, where the wind essentially ran out of momentum before it could push any farther. Voyager 2, coming in from a different direction and crossing at a different point along the boundary, encountered something else entirely on its approach, a thin layer roughly the same width as Voyager 1's stagnant zone, but with entirely different plasma properties. 2 spacecraft, 2 crossings, 6 years apart, 2 different sections of the heliopause, and 2 completely different boundary structures. Stimatios Krimigas, principal investigator for the low-energy charged particle instrument at the Johns Hopkins Applied Physics Laboratory, summed up what this meant with a clarity that captured the scientific community's reaction perfectly. Both probes, he pointed out, had encountered the heliopause at almost exactly the same distance from the Sun, 121.6 astronomical units for Voyager 1, 119 astronomical units for Voyager 2, and that alone was deeply surprising. One crossing happened near solar maximum, when the Sun's output runs high. The other happened near solar minimum, when activity is low. The heliosphere's size was expected to shift meaningfully with the solar cycle, expanding during active periods and contracting during quiet ones. Instead, both spacecraft found the boundary sitting at essentially the same distance. Krimigas said plainly that they don't understand why that is. Coming from one of the senior scientists on the mission, with decades of data behind him, that isn't a casual admission. It's a declaration that something fundamental about the relationship between solar activity and heliosphere size doesn't behave the way the models say it should. The second major surprise from Voyager 2's crossing concerned temperature. The plasma inside the heliosphere, carried outward by the solar wind, is hot, not in the everyday sense, but in the plasma physics sense, meaning its particles are moving extremely fast. Scientists expected that as this hot plasma reached the heliopause and met the colder, denser interstellar medium pressing in from outside, the temperature shift would be one of the defining features of the crossing. What Voyager 2's plasma instrument actually measured was a temperature drop far sharper than any model predicted. The plasma transitioned from the hot solar wind environment to the far colder interstellar medium across a zone narrower than expected. What made this finding especially striking was what happened with density. Solar wind plasma is relatively thin. Outside the heliopause, interstellar plasma is significantly denser. Both Voyager 1 and Voyager 2 confirm this, and together the two data points gave scientists their first ever stereo measurement of interstellar plasma density, proof that the space between stars isn't empty, but filled with plasma more than 40 times denser than the solar wind at the heliopause. But Voyager 2's measurement added something else important. The temperature of that interstellar plasma, measured directly for the first time, came in at 30,000 to 50,000 degrees Kelvin. Hot by ordinary standards, but far cooler than the plasma just inside the heliopause boundary, which the spacecraft's instruments had clocked at tens of millions of degrees. The boundary was real, the temperature contrast was real, and this direct measurement, something Voyager 1 simply couldn't provide without a working plasma instrument, gave scientists a concrete baseline number they'd previously only been able to estimate from theory. That estimate, it turned out, had been off by roughly a factor of 2. The third surprise, and the one Ed Stone, the Voyager project scientist at Caltech who had held that role since before either spacecraft launched, called the most remarkable, concerned the heliopause itself. It leaks, not metaphorically, literally. The boundary between the solar wind and interstellar space isn't a clean wall. Particles cross it in both directions. Voyager 1, on its approach, had detected what looked like tendrils of interstellar particles punching inward through the boundary from outside. Voyager 2, approaching from the south, saw the mirror image, a trickle of low-energy particles extending outward from the heliopause, leaking into interstellar space before the spacecraft had even crossed the line. That leakage was confirmed from two different entry points, at different points in the solar cycle, in different regions of the heliopause, meaning whatever was causing it wasn't a local quirk, but a genuine property of the boundary itself, something fundamental about how the heliopause works that no pre-Voyager model had accounted for. Two spacecraft, approaching from different directions 6 years apart, both found the same leaky boundary. Different mechanisms on different sides, interstellar particles pushing in on one, solar particles leaking out on the other, but the same underlying conclusion. The heliopause behaves less like a wall and more like a coastline, with surf running in both directions where two oceans meet. The Voyager probes are showing us how our sun interacts with the stuff that fills most of the space between stars in the Milky Way galaxy, Stone said in the announcement accompanying the 5 Nature astronomy papers. And the phrasing was careful and deliberate. Not how the sun ends and interstellar space begins, but how the sun interacts with interstellar space. Not a clean separation, but a continuous, messy, dynamic relationship between two environments that refuse to stay neatly on their own sides of the line. Both spacecraft, in fact, remain in a disturbed, transitional region even now, not yet in truly undisturbed interstellar space, even at 13 and 16 billion miles from the Sun. Both are still sampling an environment shaped in part by the solar system they left behind. Step back from the science for a moment and think about what Voyager 2 actually represents within the larger Voyager story, because the discoveries are only part of it. When mission planners chose Voyager 2's trajectory, the one that swept it past all 4 outer planets before heading toward interstellar space, they already knew it would arrive later, that it would cross the heliopause from a different direction than Voyager 1, and that the two spacecraft would end up offering 2 distinct views of the same boundary. None of that was accidental. Working in the 1970s with computers far less powerful than a modern pocket calculator, the Voyager team deliberately designed a 2-spacecraft mission specifically to avoid the trap of a single data point. One spacecraft can't tell you whether what it finds is typical or unusual. 2 spacecraft, approaching from different directions at different times, can begin to sketch the actual shape of the whole picture. What the planners couldn't have fully foreseen was that the instrument destined to matter most for understanding the heliopause crossing, the plasma science instrument, would fail on one spacecraft and survive on the other. That Voyager 2's plasma detector, still functioning after more than 4 decades in the radiation-soaked environment of the outer solar system, would end up supplying data Voyager 1 simply couldn't provide, closing a gap in the Voyager dataset that had existed since 1980. The division of labor between the two spacecraft was planned. The specific way it played out was not. That's the kind of science Voyager 2 represents. A planned contribution that ended up exceeding its design in ways nobody fully anticipated. A mission meant to wrap up in 1981 is instead still transmitting data in 2026, from a region of space that had never been directly sampled before, using instruments that have outlasted every prediction ever made about their working lifetime. Right now, in the summer of 2026, the JPL engineering team's attention is on Voyager 2 in a way it rarely has been before. Voyager 2 currently has 3 operating science instruments: the plasma science instrument that made the heliopause crossing measurements possible, the magnetometer, and the plasma wave subsystem, all still functioning. Together, these 3 instruments are delivering something no other asset in the history of astronomy has ever provided: a continuous, real-time, in situ measurement of conditions in the interstellar medium, taken from a spacecraft physically sitting inside that medium and moving through it at 34,000 miles per hour. But the power budget is shrinking. The same slow, mathematically inevitable decay of plutonium-238 that's steadily eating away at Voyager 1's operational capacity, stripping 4 watts of available power from the spacecraft every year, is doing the identical thing to Voyager 2. At launch, each spacecraft drew roughly 470 watts from its 3 radioisotope thermoelectric generators. Today, Voyager 2 has slightly more power left than Voyager 1, which is exactly why it still runs 3 instruments, while Voyager 1 is down to 2, following the shutdown of its low-energy charged particle instrument in April 2026. But that margin isn't large, and it's shrinking by 4 watts a year, same as always. The Big Bang procedure is meant to change that math. As described by NASA's Jet Propulsion Laboratory, it involves swapping out a whole cluster of powered devices at once, switching some off entirely and replacing others with lower power alternatives, to keep the spacecraft warm enough to keep collecting science data. The name comes from the all-at-once nature of the reconfiguration, not one change at a time, tested and verified before moving to the next, but everything simultaneously, a complete restructuring of how power flows through every remaining active system, attempted in a single coordinated operation, across a communication link where each command takes more than 16 hours to arrive, and each response takes more than 16 hours to return. The reason for doing it all at once, instead of incrementally, comes down to the risk of intermediate states. During any power system reconfiguration, there are transitional moments where the system sits in neither its old configuration nor its new one. And those moments can trigger fault protection systems, automated safety mechanisms built into both spacecraft that will start shutting components down on their own the instant they detect power draw exceeding what the generators can supply. The entire point of the Big Bang is to minimize time spent in those dangerous in-between states by making every change at once, sprinting through the transition as fast as possible. If it works, if the new power distribution genuinely trims enough waste to recover meaningful headroom in the power budget, it could extend the operational life of Voyager 2's remaining instruments by at least a year, possibly longer. And if the Big Bang succeeds on Voyager 2, the same procedure is slated to be attempted on Voyager 1 no earlier than July 2026, with hopes that success there might even allow the low-energy charged particle instrument, shut down back in April, to be switched back on. Voyager 2 goes first, not because it matters less, but because it sits slightly closer to Earth, has slightly more power in reserve, and is therefore the safer test subject for a procedure that's never been attempted before at this range. What's actually at stake in keeping Voyager 2's instruments alive as long as possible isn't a question with one simple answer. It's several layered questions, each pointing to a gap in human knowledge that only these 2 spacecraft can currently fill. The structure of the heliosphere is one of them. The 5 2019 Nature Astronomy papers established that the heliopause leaks, that it sits at roughly the same distance from the Sun, regardless of solar activity, that interstellar plasma on the far side is denser and cooler than expected, and that the boundary structure looks different depending on which direction you approach from and which instruments you're carrying. But those findings raised at least as many questions as they answered. Why does the heliopause sit at the same distance during both solar maximum and solar minimum? What actually determines where the boundary sits, if not the strength of the solar wind? What's driving the two-way leakage of particles, and how does that leakage shift over time as the sun travels through different regions of the galaxy's interstellar medium? The overall shape of the heliosphere remains genuinely uncertain, too. Some models predict a long, comet-like tail stretching away from the sun in the direction opposite its motion through the galaxy. Others suggest something closer to spherical, or even lemon-shaped. Voyager 1 and Voyager 2 are sampling two separate points along the heliosphere's outer edge, one roughly toward the nose, one toward the flank. And their combined data is one of the primary tools scientists have for testing these competing models. The longer both spacecraft keep operating, the more data accumulates, and the tighter those models can be constrained. The interstellar magnetic field is another open question entirely. Both spacecraft have measured the magnetic field in interstellar space beyond the heliopause, and the direction of that field carries implications for how the heliosphere is oriented relative to the galaxy's large-scale magnetic structure. Voyager 2's magnetometer, still functioning in 2026, continues contributing measurements that help map the local interstellar magnetic field in the heliosphere's southern hemisphere, a region distinct from where Voyager 1 is sampling in the north. Underneath all of these specific scientific questions sits a bigger issue. What happens when both spacecraft eventually fall silent? There is no replacement waiting in the wings. No follow-on mission is currently sitting in interstellar space. There's no instrument within 50 billion miles of where these two spacecraft currently sit, and there won't be for decades. When the last of their instruments finally goes dark, the map they've been drawing of the interstellar medium simply stops being updated, and every question they raised but couldn't fully answer will remain open until some future mission, not yet funded, not yet designed, not yet approved, eventually retraces the journey and reaches the same boundary. Voyager 2's list of achievements is almost too long to fully absorb. It remains the only spacecraft ever to visit Uranus, and during its January 1986 flyby, it discovered 10 previously unknown moons and 2 new rings around the planet. It measured Uranus's extreme axial tilt of 97.77 degrees and its interior composition as an ice giant, and it found a magnetic field so wildly offset from the planet's rotation axis that it still challenges current models of how planetary magnetic fields form. It's also the only spacecraft ever to visit Neptune. During its August 1989 flyby, the Voyager program's final planetary encounter, it discovered 6 new moons, including Proteus, a body large enough that it arguably should have been spotted from Earth long before Voyager arrived. It measured Neptune's supersonic winds, clocked at 1,500 miles per hour, the fastest winds recorded anywhere in the solar system at the time. And it delivered detailed observations of Neptune's largest moon, Triton, revealing active nitrogen geysers shooting material 5 miles into the thin atmosphere and establishing that Triton was almost certainly a captured Kuiper Belt object, a world that formed elsewhere entirely and was later pulled into Neptune's orbit by gravity, its surface reshaped by tidal heating from an orbit that's been slowly circularizing ever since. Voyager 2 also discovered a 14th moon at Jupiter during its 1979 flyby. It gathered data on Saturn's rings, revealing a complexity of structure invisible to Earth-based telescopes. It confirmed the active volcanic eruptions on Io first spotted by Voyager 1, catching the volcano Prometheus mid-eruption in a plume of sulfur dioxide frost, rising 125 miles high. And it returned images of Europa's icy surface, the fracture patterns, the scarcity of large craters, the reddish-brown material staining the cracks between ice blocks, that first hinted at a liquid water ocean hiding beneath the ice, images that seeded decades of scientific interest in Europa as a possible habitat for life, and eventually helped inspire the Europa Clipper mission currently underway. All of this from a spacecraft launched on August 20th, 1977, 49 years ago now, built with technology from an era before the internet, before personal computers, before GPS, before cell phones, and designed to last just 4 years. It's still transmitting, still gathering data, still delivering, thanks to the unique route it was handed and the one instrument that survived where Voyager 1's identical counterpart failed, something no other spacecraft in history has ever supplied. Direct measurements from inside interstellar space, taken from a different direction than Voyager 1, using a functioning plasma instrument for the first time ever.